For the final project, we decided to re-implement a popular paper on novel view synthesis. Previous works by various authors proposed different approaches of view rendering techniques. The two related architectures shown on the slide have a few drawbacks. They are either hard to train or not able to synthesize of photorealistic views. A neural radiance field, NeRF, is a fully connected neural network that can generate a photorealistic novel views of a complex 3D scenes based on a partial set of 2D images. It is trained to use a rendering loss to reproduce unseen views of a scene. It works by taking input images representing a scene and interpolating between them to render one complete scene. As a part of our implementation, we will talk about the essential parts of NeRF architecture. Namely, we will discuss hierarchical sampling, positional encoding, and MLP architecture. The first step of NeRF architecture is to feed input data points to the neural network. The input data is obtained by shooting a ray into each pixel of each image of a rendering scene. First, we uniformly distribute points within the range of bounding box. Then, depending on the weights of each point, we will resample the region that makes most contribution to the rendering of the scene. The latter step of resampling the region at points that have the most contribution is known as hierarchical sampling. In order to increase the quality of rendered images, we implement the positional encoding. Positional encoding could be best summarized by the following formula. The purpose of positional encoding is to map an input into a higher dimensional space, where MLP can more easily approximate higher frequency functions. On your screen you can see visualization of NeRF's fully connected network architecture. Input vectors are shown in green, intermediate layers are shown in blue, output vectors are shown in red, and the number inside each block signifies the vector's dimension. All layers are standard fully connected layer. Black arrows indicate layers with ReLU activation. Orange arrow indicates a layer with no activation. Dashed arrow indicates a layer with sigmoid activation, and the plus sign denotes the vector concatenation. In order to optimize the neural network at each iteration, we try to minimize the total squared error between rendered and true pixel color. The MLP outputs volume density and RGB value of each point on array. The main evaluation metric to compare original paper results and our implementation is PSNR. The PSNR computes the peak signal-to-noise ratio between two images. This ratio is used as a quality measurement between the original and rendered image. The higher the PSNR, the better the quality of the reconstructed image. During our implementation, we were able to achieve values close to the original paper. On this slide, you can see the visual results of NeRF. The ground truth is the left image under each scene, while right image corresponds to rendered view. As we can see, we were able to achieve successful reconstruction of the unknown scene. It is necessary to note that the novel scene shows important geometry, along with position features. For example, we can see two synthesized images of the Lego truck from different views. Along with the geometry details, we can see the shadows of the respective scenes, which show clear dependency of the rendered scene on the position of the camera. On the final note, NeRF introduced a novel way of the 3D scene reconstruction. The biggest difference between the NeRF model and traditional neural networks for 3D reconstruction is that the NeRF implicitly represents the object and generates photorealistic views. However, it requires a significant number of images of the same object, and camera pose of each image is required. Thus, the training time is very long. Overall, NeRF model shows promising prospect in photorealistic view synthesis and definitely has more avenues for future research. Thank you for your attention.